Hello, and have a good day, everyone. So now we continue with our new chapter, okay, which is chapter number 10 in managerial economics. So we will discuss chapter 10's game theory inside oligopoly, right? So in this chapter, we continue our analysis of strategic interaction. Okay? Still remember, right? In chapter 9, we saw about the strategic interaction. Okay, as we saw in chapter 9, when only a few firms compete in a market, and the action of one firm will have a drastic impact on its rival. For example, the pricing and output decision of one firm in an oligopoly generally will affect the profit of other firms in the industry. So consequently, to maximize a profit, a manager must take into account the likely impact of his or her decision on the behavior on the other managers in the industry. So in this chapter, we will delve more deeply into managerial decision that arise in the presence of interdependence. So we will develop general tools that will assist you in making a host of decisions in oligopolistic market, including what price to charge, how much advertising to use, whether to introduce new products, and whether to enter a new market. So the basic tool we will use to examine this issue is game theory. So game theory is a very useful tool for managers. In fact, we will see the game theory can be used to analyze decisions within a firm, such as those related to monitoring and bargaining with workers, right? This is an overview of this topic, introduction to game theory. Okay, simultaneous move, one-shot games, infinitely repeated game, and multi-stage games. Right. So perhaps when you think of a game, a trivial game like tic-tac-toe, checker, or wheel of fortune comes to mind. So game theory is actually a much more general framework to aid in decision making when your payoff depend on the action taken by other players. So in a game, the player are individual who make a decision. For example, in an oligopolistic market consisting of two firms, okay, each of which must make a pricing decision. So the firms are more pricely, the firm's manager are the players. So the plans decision of players are called strategies. Plans called strategies. So plans players plan decision, we call it as a strategy. Yeah. So payoff to players are the profit or loss resulting from strategies. So in the analysis of game, the order in which players make decision is very important. So in a simultaneous move game, each player makes decision without knowledge of the other player's decision. In a sequential move game, one players make a move after observing the other player's move, right? So it is important to distinguish between one shot game and a repeated game. So in one shot game, the underlying game is play only once. In a repeated game, the underlying game is play more than once. Okay. For example, if you agree to play one and only one game of chess with a rival, you are playing a one shot game. if you agree to play chess two times with a rival, so you are playing a repeated game, right? So before we formally show how that game theory can help managers solve the business decision, it is instructive to provide an example. Imagine that two gasoline stations are located side by side on the same block, so that neither firm has a location advantage over the other. Yeah. So consumers view the gasoline at each station as perfect substitute, yeah, and will purchase from the station that offers the lower price. So the first thing in the mornings, the manager of a gas station must phone the attendant to tell him what price to put on the sign. Okay. So since she must do so without knowledge of the rival price, this pricing game is simultaneous move game. So this type of game often is called the Bertrand-Dupuy game. So order of play is important. So that's what you call as simultaneous move game. Each player makes decision with knowledge of other player decision, and sequential move game. One player observe its rival move prior to selecting strategy. Then this frequency of rival interaction. So one shot game, so as we explained just now. Yeah, game is play once, and a repeated game if you are looking to play two times, like for example to play chess. So this is a simultaneous move. Okay, one shot games or normal form game. So a normal form game consists of a set of players, where n is a finite number. Okay, and each player's strategy set of feasible action consists of a finite number of strategies. So to analyze, to be used, the basic tool to use to analyze the simultaneous move one shot game. Recall that in a simultaneous move game, a player must make a decision without knowledge of the decision made by the others. So the fact that the game is one shot simply mean that the player will play the game only once. So knowledge of simultaneous move one shot game is important for two managers making decision in an environment of interdependent. For example, it can be used to analyze situation where the profit of a firm depend not only on the firm's action but on the action of rival firms as well. So before we look at specific application of simultaneous move one shot games, let us examine the general theory used to analyze that such this decision. So we begin with two definitions. First, a strategy. That's is a decision rule. Decision rule that describe the action a player will take at each decision point. The second one is the normal form game. Indicate the player in the game. So the possible strategies of the player and pay off to players that will result from alternative strategy. So perhaps the best way to understand precisely what is meant by strategy and normal form game is to examine a simple example. So the normal form of simultaneous move game is presented in this table. Okay, the normal form game. Okay. So there are two player whom we call as A and B to emphasize player A and B, right? Yeah, to emphasize that theory is completely general. That is, the player can be only two entities, okay, that are engaged in a situation of a strategic interaction. So if we wish, you may think of a player as the managers of two firms competing in duopoly. So player A has two possible strategies. Two possible strategies. He can choose up or down. He can choose up or down. Similarly, the feasible strategy for player B are left or right. So this illustrates that the player may have different strategic option. Again, by calling the strategies up, down, and so on, we emphasize that this action can represent virtually any decision. For instance, up might represent raising the price, and down or lowering price, or up maybe high level of advertising, and down low level of advertising. So it can be anything. That's refer to up and down. So finally, the payoff to the two players are given by the entries in each cell of the matrix. For the first entry refer to the payoff to player A, and the second entry denotes the payoff to player B. So an important thing to notice about description of a game is that the payoff to player A crucially depend on the strategy player B chooses. For example, if chooses up and B chooses left, A chooses up and player B chooses left. Okay, so the result payoff are 10 for A and 20. Okay, 10 for A, okay, and 20 for B. Okay, so similarly, if players A strategy is up while B strategy is right, so A's payoff is 15, and while B payoff is 8. Okay, so since the game in table 10.1 is simultaneous move, so one shot game, so the player gets to make one and only one decision and must make their decision at the same time. So for player A, the decision is simply up or down. Okay. So moreover, the player cannot make conditional decision. For example, A can choose up if B choose right or down. So if B choose left. So the fact that the player make decision at the same time precludes each player from basing his or her decision on what the other player does. So what is the optimal strategy for a player in simultaneous game, one or simultaneous move, one shot game? So as it turned out, this is very complex question and depend on the nature of the game being played. So there is one instance, however, in which it is easy to characterize the optimal decision. So a situation that involves a dominant strategy. So a strategy is a dominant strategy if it results in the highest payoff regardless of the option of the opponent. So in table 10.1, the dominant strategy for A is up. To see this, note that if player B choose left, so the best choice by player is up, since 10 unit of profit are better than minus 10, right? So 10 unit of profit is better than minus 10. Okay. So if B choose right, the best choice of A would be up since 15 unit of profit are better than 10. So he would earn by choosing down. So in short, regardless of whether player B strategy is left or right, okay, so the best choice by player A is up. Up is a dominant strategy. In this case, so up is a dominant strategy, for player A. Okay. So in simultaneous move one shot game where a player has a dominant strategy, so the optimal decision is to choose the dominant strategy. So by doing so, you will maximize your payoff regardless of what your opponent does. So in some games, a player may not have a dominant strategy. So what should a player do in the absence of a dominant strategy? So one possibility would be to play a secure strategy. Okay, so that's a strategy that guarantee a highest payoff given the worst possible scenario. So as we will see in a moment, so this approach is not generally the optimal way to play a game, but it's useful to explain the reason that underlies this strategy. So by using a secure strategy, okay, a player maximize the payoff that would result in the worst case scenario. So in other words, to find a secure strategy, a player examine the worst payoff that could arise for each of his or her action and chooses the action that has the highest of this worst payoff. So while useful, the notion of secure strategy suffer from two shortcomings. First, it is a very conservative strategy and should be considered only if you have a good reason to be extremely averse to risk. Second, it does not take into account the optimal decision of your rival, so and thus may prevent you from earning a significantly higher payoff. So in particular, player B in table 10.1, you can see here, table B should recognize that a dominant strategy for A is to play up. Thus, player B should reason as follow. Player A will surely choose up since up is a dominant strategy. Therefore, I should not choose my secure strategy or right. My secure strategy or right, okay, but instead choose a left. Okay. So assuming player A indeed chooses the dominant strategy up, so player B will earn 20 by choosing left, but only 8 by choosing the secure strategy on the right. Okay. So a very natural way of formalizing the end result of such a thought process is captured in the definition of what we call as a Nash equilibrium. So Nash equilibrium, so we will see a few of example after this. Okay, so a set of strategies constitute a Nash equilibrium if given the strategy of the other players. So no player can improve her payoff by unilaterally changing her own strategy. So the concept of Nash equilibrium is very important because it represents a situation where every player is doing the best he or she can given what other players are doing, right? So let us now see how that game theory can help formalize the optimal managerial decision in a veteran duopoly. Okay. Consider the game presented in this table, okay, table 10/2, where two firms face a situation where they must decide whether to charge low or high prices. So the first number in each cell represent firms A. Okay, the first number, okay, first number like 0, 50, minus 10 and 10, that's represent firms A profit, and the second number represent the firms B profit, like 0, minus 10, 50 and 10, right? That's represent the B firms B profit. Okay, For example, if firm A charges a high price while firm B charge a low price, so a losses of 10 unit of profit. Okay, A losses 10 unit, you can see minus 10, okay, whilst 10 unit of profit, while B earn 50 unit of profit. So while the number in table 10 slash 2 are arbitrary, so their relative magnitude is consistent with the nature of Bertrand competition. So in particular, note that the profit of both firms are higher when both charge high prices than when they both charge low prices, because in each instance, okay, consumer have no incentive to switch to the other firm. So on the other hand, if one firm charge a high price and the other firm undercut the price, so the lower price firm will gain all the other firms customers, and thus earn higher profit at the expense of the competitor. So we are considering a one shot play of the game in table 10.2. That is a situation where the firm meet once, only once in the market. Moreover, the game is a simultaneous move game in that each firms makes a pricing decision without knowledge of the decision made by the other firm. So in a one-shot play of the game, a Nash equilibrium strategies are for each firm to charge the low price. So the reason is simple. If firm B charge a high price, a firm A best choice is to charge a low price, since 50 units of profit are better than 10 units. So it will earn if A charge the high price. So similarly, if firm B charge the low price, firms A, okay, best choice is to charge the low price, since it's 0 units of profit are preferred to the 10 units of losses. So that's would result if A charge the high price. Similar argument hold from firm B's perspective. So firm A is always better off charging the low price regardless of what firm B does, and B is always better off charging the low price regardless of what A does. Hence, charging low price is a dominant strategy for both firms. So to summarize in one short version of this game, each firm best strategy is to charge a low price regardless of the other firm's action. So the outcome of the game is that both firms charge low prices and earn a profit of 0. So clearly, profit are less than firms would earn if they colluded and agreed to both charge high price. For example, in this table 10.2, we see that each firm would earn profit of 10 units if both charge high price. Okay, so this is a classic result in economics, and it's called a dilemma because the Nash equilibrium outcome is inferior from the viewpoint of the firms to the situation where they both agree to charge high prices. So why can't firms collude and agree to charge high price? So one answer is that collusion is illegal in certain place. So firms are not allowed to meet and conspire to set high prices, right? So there are other reasons. However, suppose the manager did secretly meet and agree to charge high price, would they have an incentive to live up to their promises? So consider firms A point of view. If it cheated on the collusion agreement by lowering its price, so it would increase its profit from 10 to 50. Okay? So thus firm A has an incentive to induce firm B to charge a high price so that it can cheat to earn higher profit. So of course firm B recognize this incentive, which preclude the agreement from being reached in the first place. So however, suppose the manager of firm A is honest and would never cheat on a promise to charge a high price. So she is honest enough to keep her own word to the other manager, but not too honest as to obey the law against collusion. So what happened to firm A if manager of firm B cheats on the collusive agreement? So if B cheats, A experiences losses of $10. So when firms A stockholders ask the manager why they lost $10 when the rival firm earned a profit of $50, so how can the manager answer? So she cannot admit she was cheated on in a collusive agreement. For doing so might send her to jail for having violated the law. So whatever her answer, she risks being fired or sent to the prison. Okay. So our framework for analyzing simultaneous move, one shot game, one shot game can also be used to analyze advertising and quality decision. Okay, for advertising and quality decision. So in oligopolistic market, firms advertise and increase their product quality in an attempt to increase the demand for their product. So while both quality and advertising can be used to increase the demand for product, our discussion will use advertising as a placeholder for both quality and advertising. So an important issue in evaluating the consequences of advertising is to recognize where to increase in demand comes from. So in a most oligopolistic market, advertising increases the demand for a firm's product by taking customer away from other firm in the industry. So an increase in one firm advertising increase its profit the expense of other firm in the market. So there is interdependency among the advertising decision of firm. So a classic example of such a situation is the breakfast cereal industry, which is highly concentrated. So by advertising its brand of cereal, a particular firm does not induce many consumer to eat cereal for lunch and dinner. Instead, it induces a customer to switch to its brand from another brand. So this can lead to a situation with each firm advertise just to cancel out the effect of other firms. So advertising resulting in high level of advertising, no change in industry or firm demand, and low profit. So thus far, our analysis of oligopoly has focused on situation where firm have competing objective. One firm can gain only at the expense of other firm. So not all game have this structure, however. Imagine a world where producer of electrical appliance have a choice of which type of electrical outlet to put an appliance. So in table uh, okay, for 10.4, this is the coordination decision. Right? Let's say for producer of electrical appliance, in an environment where different appliance require different outlet. So a customer who desire several appliances would have to spend a considerable sum wiring the house to accommodate all the appliances. So this would reduce the amount that the consumer has available for buying appliances, and therefore would adversely affect the profit of appliance manufacturers. So in contrast, if appliance manufacturers can coordinate their decision, that is produce appliances that require the same type of wiring, so they will earn higher profit. Okay. So in in table for 10.4 represent a hypothetical example of what is called a coordination game. Coordination game. So two firms must decide whether to produce appliance requiring 120 volt or 90 volt outlets. So if each firm produce appliance requiring 120 volt outlets, so each firm will earn profit of $100. So $100. Similarly, if each firm produces appliances requiring 90 volt outlet, so each firm will earn also $100. So however, if the two firm produce appliance requiring different type of outlet, so each firm will earn zero profit. Zero profit. Okay, due to the lower demand that will result from consumers need to spend more money wiring their houses. So what would you do if you were the manager of firm A in this example? So if you do not know what firm B is doing is going to do, you have a very tough decision. Okay, all you do is guess what B will do. So if you think B will produce 120 volt appliances, you should produce 120 volt appliances as well. Okay, if you think B will produce 90 volt appliances, so you should do likewise. So you will thus maximize profit by doing what firm B does. So effectively, both you and firm B will do better by coordinating your decision. Okay, by coordinating your decision. So the game in table 10.4 has two Nash equilibria. So one Nash equilibrium is for each firm to produce 120 volt appliances. So the other is for each firm to produce 90 volt appliances. So the question is how the firms will get to one of these equilibria. If the firms could talk to each other, so they could agree to produce 120 volt systems. Alternatively, the government could set a standard that electrical outlets be required to operate on 120 volt. So two prongs outlets. So in effect, this would allow the firm to coordinate their decision. Okay. Notice that once they agree to produce 120 volt appliance, there is no incentive to cheat on this agreement. So the game is stable. 10.4 is no analogous to the pricing or advertising games analyzed earlier. It is a game of coordination rather than a game of conflicting interests. Okay. So game theory also be used to analyze interaction between workers and the manager. Between workers and the managers. So in chapter 6, we discussed the principal agent problem, right? And argue that there can be conflicting goals between workers and managers. So managers desire worker to work hard while workers enjoy leisure. So in our discussion of manager worker principal agent problem in earlier chapter, we noted that one way a manager can reduce workers incentive to shirk is to engage in random spot check of the workplace. So game theory provide a way of seeing why this can work. So consider a game between a worker and a manager. So the manager has two possible action. The first one is monitor the worker. The second one, don't monitor the worker. Alright? The first one is monitor, and then the second is don't monitor. And then the worker has two choices. Okay? The first one work. The second is shirk. Okay? These possible actions and resulting payoff are depicted in this table. Table 10, 5. Right? So the interpretation of this normal form game is as follows. If the manager monitor while the workers work, so the workers win and the manager lost. So the manager has spent time monitoring a worker who was already working. So in this case, suppose the manager payoff is -1, okay, and the workers payoff is 1. So the payoff are the same if the manager does not monitor and the worker shirk. So the workers wins because she get away with shirking. So in contrast, if manager monitors while the worker shirks, so the manager wins 1 and the workers who get caught lost 1. So similarly, if the worker work and the manager does not monitor, so the manager wins 1 and the worker loses 1. So the number in table 10.5 are of course purely hypothetical, but they are consistent with the relative payoff that arise in such situation. Okay, so notice that the game in table 10.5 does not have a Nash equilibrium, at least in the usual sense of the term. To see this, suppose the manager's strategy is to monitor the worker. So then the best choice of the worker is to work. So but if the workers work, the manager does better by changing his strategy. So like choosing not to monitor. So thus monitoring is not part of a Nash equilibrium strategy. The paradox, however, is that not monitoring isn't part of Nash equilibrium either. To see why, suppose the managers don't monitor, then the worker will maximize her payoff by shirking. Given that the worker shirks, the manager does better by changing the strategy to monitor to increase his payoff by -1 to 1. So thus we see that don't monitor is not part of a Nash equilibrium strategy either. Okay. So the things to notice in this example is that both the worker and the manager want to keep their action secret. Okay. If workers knows that the worker is doing, it will be okay, curtains for the worker and vice versa. So in such a situation, okay, players find it in their interest to engage in the mix or randomized strategy. So what this means is that players randomize over their available strategy. For instance, the manager flips a coin to determine whether or not to monitor. So by doing so, the worker cannot predict whether the manager will be present to monitor her and consequently cannot outguess the manager. So those of you who have taken multiple choice tests have had first-hand experience with randomized strategy. If maybe your lecturer or your teacher made A the correct answer more often than B, C, or D, so you could gain by answering A is those instances when you did not know the correct answer. So this would enable you to earn a higher grade than you deserve based on your knowledge of subject matter. So to prevent this strategy from working for you, maybe your teacher or your professor randomize which option is the correct answer, so that you cannot systematically guess the correct answer on the exam. Okay. And then the final application of simultaneous move, one shot game, we will consider is a simple bargaining game. So in a Nash bargaining game, two players bargains over some object of value. So in simultaneous move, one shot bargaining game, the player have only one chance to reach an agreement, and the offer made in bargaining are made simultaneously. Okay. To be concrete, suppose management and a labor union are bargaining over how much of a $100 surplus to give to the union. Okay, suppose for the simplicity, that's the $100 can split only into 50. Okay, so the player have one shot to reach an agreement. Okay, the parties simultaneously write the amount they desire on a piece of paper, like 0, 50 or 100. Okay, if the sum of the amount each party asks for does not exceed 100, okay, so the player get the specified amount. But if the sum of the amount requested exceed $100, so bargaining end in a stalemate. So let's suppose that the delay caused by this stalemate cost both the union and management $1. So in table 10.6, present the normal form of this hypothetical bargaining game. If you were management, what amount would you ask for? Suppose you wrote down 100, you wrote down $100. So then only way you would get any money is if the union asks for 0. Okay, if the union asks for 0, right? So notice that if management asks for 100 and the union asks for 0, neither party would have an incentive to change its amount. So we would be in Nash equilibrium. So before concluding that you should ask for $100, think again. Think again. Suppose the union wrote down 50. Okay? So management best response to this most move would be to ask $50. And given that management asked for $50, the union would have no incentive to change its amount. So thus a 50-50 split of 100 also would be a Nash equilibrium. So finally, suppose management asks for $0 and the union asks for the entire $100. So these two would constitute a Nash equilibrium. Neither party would improve its payoff by changing its strategy given the strategy of the other. So thus, there are 3 Nash equilibrium outcomes to this bargaining game. One outcome splits the money evenly among the parties, while the other 2 outcomes give all the money to either the union or management. So this example illustrates that the outcome of simultaneous move bargaining game are difficult to predict because there are generally multiple Nash equilibria. So this multiplicity of equilibria leads to inefficiencies when the parties fail to coordinate and on an equilibrium. So in table 10.6, for instance, 6 of the 9 potential outcomes are inefficient in that they result in total payoff that are less than the amount to be divided. So three of these outcomes entail negative payoff due to the stalemate. Okay. So unfortunately, stalemate is common in labor dispute. Agreements often fail or are delayed because the two sides ask for more. In total, there is to split. So experimental evidence suggests that bargainer often perceive a 50-50 split to be fair. So consequently, many players in real world setting tend to choose strategies that result in such a split even though there are other Nash equilibria. So clearly the game in table 10.6, if you expect the union to ask 50, you as a management should ask $50 as well. So now consider the simultaneous move veteran pricing game presented in this table 10.0. Okay, the Nash equilibrium in one short play of this game is for each firm to charge low price and earn zero profit. So let us suppose the firm play the game in table 10.0 day after day, so week after week, for all eternity. So thus we are considering an infinitely repeated veteran pricing game, so not a one shot game. So in this section, we will examine the impact of repeated play on the equilibrium outcome of the game. So when firms repeated face a payoff metric such as that in table 10.0 10.7, so it is possible for them to collude without fear of being cheated on. So they do this by using a trigger strategies. Using a trigger strategies. Okay. So a trigger strategy is a strategy that is contingent on the past play of player in a game. So in a player who adapt a trigger strategy continues to choose the same action until some other player takes an action that triggers a different action by first player. Okay. To see how trigger strategies can be used to support collusive outcomes, suppose firm A and B secretly meet and agree to the following arrangement. So we will each charge the high price, provided neither of us has ever cheated in the past. Okay. If one of us cheat and charge the low price, so the other player will punish the deviator by charging the low price in every period thereafter. So thus, if firm A cheats, it pulls a trigger that leads firm B to charge the low price forever after, and vice versa. So this turned out that if both firms adapt such a trigger strategy, they are conditions under which neither firm has an incentive to cheat on the collusive agreement. So before we show this formally, let's examine this basic intuition. If neither firm in table 10.7 cheat on the collusive agreement, each firm will earn $10 each period forever. So, but if one firm plays according to the agreement, so the other firm could cheat and earn an immediate profit of $50 instead of 10. Thus, there is still the immediate benefit to a firm of cheating on the agreement. However, because the firm compete repeatedly over time, so there is a future cost of cheating. According to the agreement, if a firm ever cheat, so the other firm will charge a low price in all future period. Thus, the best the firm that cheated can do is earn $0 in the period after cheating. Instead of $10, it would have earned had it not broken the agreement. So in short, the benefit of cheating today on the collusive agreement is earning $50 instead of $10 today. But the cost of cheating today is earning $0 instead of $10 in each future period. So if the present value of the cost of cheating exceed the one-time benefit of cheating, so it does not pay for a firm to cheat and high price can be sustained. Okay. So in summary, in one short game, there is no tomorrow. Any gain must be had today or not at all. So in an infinitely repeated game, there is always tomorrow. And firms must weigh the benefit of current action against the future cost of those actions. So the principal result of infinitely repeated game is that when the interest rate is low, so firms may find it is in their interest to collude and charge high price, unlike in the case of one-shot game. So the basic reason for this important result in this, if a player deviate from the collusive strategy, he or she is punished in future period long enough to wipe out their gain from having deviated from the collusive outcome. So the threat of punishment makes cooperation work is in repeated game. So in one short game, there is no tomorrow, and the threat have no bite. So it is easier to sustain collusive agreement via punishment strategies outlined earlier when firms know first who their rival, and so they know whom to punish should the need arise, and then the second who are their rival customer, so that if punishment is necessary, they can take away those customers by charging lower price. And when their rival deviate from conducive agreement, so they know when to begin the punishment. So furthermore, the must be able to successfully punish rival for deviating from the collusive agreement. So otherwise, the threat of punishment would not work. So those factors are related to several variables reflected in the structure and conduct the industry. The first one is number of firm. First one is number of firm, right? So collusion is easier when there are few firm rather than many. If there are n firm in industry, so the total amount of monitoring that must be go on to to sustain the collusive agreement. Okay. So for example, let's the firm be indexed by A, B, C, and so on. So if there are only two firms in the industry, then to punish a firm for deviating, each firm must know whether its rival has deviated, and if so, where its customer are, so it can punish the rival by getting some of its customer. So to do this, each must keep an eye on its rival. So with two firms, this information may obtain if A monitor B and B monitor A. Okay. So total number of monitors need in the market grows very rapidly as the number of firm increases. So for example, if there are 5 firms, each firm must monitor 4 other firms. So the total number of monitors needed in the market is 5 times 4 equal to 20. So the cost of monitoring rival reduces the gain to colluding. And then the second factor you can see from here is a firm size. So economies of scale exist in monitoring. Okay, monitoring and policing cost constitute a much greater share of total cost for small firm than for larger firm. So thus it may be easier for a large firm to monitor a small firm than for a small firm to monitor a large firm. For example, a large firm, we say 20 outlets, can monitor the prices charged by a small competitor with one outlet. So by simply checking prices at one store, but to check the price of its rival, the smaller firm must hire individual to monitor up to 20 outlets. Okay, and then this other factor is history of the market. So one key issue not addressed thus far is how firm reach an understanding to collude. So one way is for the firm to explicitly meet and verbally wants their rival not to steal their customers. So or else they will be punished. Alternatively, firms might not meet at all, but instead gain an understanding over time of the way the game is played, and thus achieve tacit collusion. So tacit collusion occur when the the firms do not explicitly conspire to collude, but accomplish collusion indirectly. So for example, in many instances, firm learn from experience how other firm will behave in a market. And then Another last factor is a punishment mechanism. So the pricing mechanism firm use also affect the ability to punish rival that do not cooperate. For example, in a posted price market, where a single price is posted and charged to all of firm's customer, so the cost of punishing an opponent is higher than in market in which different customer are quoted different prices. So the reason is as follow: if a single price is charged to all customer, so a firm that wishes to punish a rival by stealing its customer not only has to charge a low price to the rival customer, but also must lower its price to its own customer. So this is essentially what a retailer must do to get customer away from another retailer. Okay? So in contrast, in an industry in which different prices are quoted to different customer, a firm can punish its rival by charging the rival customer a low price while continuing to charge its own customer a higher price. So this, of course, substantially reduces the cost of engaging in punishment. Okay. Okay, that's for part one on this chapter. We will continue in the part two after this.